Hello Marta, sorry for not being able to submit the assignment so long, partly because of the bad weather. You can see after 3 days the weather is still, well, it is quite raining and then there's a power cut. But I lost my work, I have done it once again, part of it. I don't think it will be fruitful of me doing all these integrate calculations. But yeah, after I make and you get the video and you don't understand, you have the right to ask me questions of how to do one part or an integrate part. Partly also because some of these calculations are readily available on the web, so much so that I do one version and that's also out there somewhere or the other. The Greek letters are limited and multiple people ask these questions. So let's stick to work, because that's me charging extra from you to do a copied work is not fine, but I'll definitely show you how to do one A and B over these videos so that you can try it yourself, and if you can't, then ask me specific questions and I'll be glad to help them. I have these ready, so let's start. So what you can see on the screen, the first question, part A, tells us verify the following distributions belongs to the exponential family. Now, first of all, you need a standard version of an exponential family to start with. So, well, I chose this. There are various versions. There could be a version available in class, but definitely it will be some kind of a function of y and theta, which we have given here, minus b of theta. This is optional. Sometimes people include this in s of, because sometimes people include this as s of y and b of theta and leave this out, but you can keep it, plus c of y comma phi. Some people add extra terms, d of y, but that essentially comes here. So this is the version I'm using. It's an acceptable formula for the exponential family. And then what I start with here is, you need one definition of the exponential family. You need to by heart this, so that this is this part. Oh, this part is your is something that you need to by heart. This definition will be useful every time when you are thinking about exponential family. Now we start with the first line here. The first line, which is, so I just copied this formula of the probability mass function, put it on paper. The second is, you take a log of it, because you need it in this form. So how to reach that form? You can't keep it in compound form. You have to dissociate these terms. So you take a log of it. That's the way. So when you take a log of these terms will dissociate. So you can see log and cy. You will see n log, which is basically breaking this up, n log 1 minus pi, and then I have taken y log pi and y log 1 minus y log 1 minus pi into one term, and then I get this term, which confronts y into theta. So we have a y, we have a theta, minus b of theta by a phi, and we have a c term. So that's why I was asking you to concentrate on this, because this part of the definition, is where you want to lead your terms towards. So I have a phi, I have a theta, I have a b of theta, and I have a c term. And for that I had to take logarithms, and then exponential of logarithm is the function itself. Log is invertible. That's how we call it. You must be familiar with these terms. So we have an exponential term out here, and yeah, that's pretty much the form. And then then comes the particular part, which is setting theta equals to what? So y into theta, so y into log. So this is the theta, so setting theta equals to log of this. B of theta equals to, so 1 minus pi, what we do here. You have to check out that minus beta equals to, this should be an equal to, B of theta equal to minus n log n into log. So this is, don't confuse it for something else, this is n into log, and this is n into log of 1 minus pi. Why are we doing this? Because I want to make this b of theta, but once I've defined theta, I'll have to define b of theta, which is this part, in terms of theta, which is this part. Okay, so when I have to say 1 minus pi, so we wanted it plus n1 minus pi, so this is actually backing out, so I make it minus minus of n log of 1 minus pi, and then when it's log 1 minus pi, I can say it's 1 by 1 minus pi, which comes to, so if it's 1 by 1 minus pi, this is equals to 1 plus pi by 1 minus pi. Yeah, 1 by 1 minus pi is equal to 1 by 1 plus pi by 1 minus pi. So take this, you come here, and then you go to here. That's a bit of back calculation, the dirty stuff. And then we of course keep our other variables. So I say psi is 1, a of psi is 1, c of log n, c of y comma phi equals to c of y comma 1 equals to log n combined y. Nothing much of substance there, it's more of the strategy, the back calculations out here, and this is where we had to reach. So then we do it for the gamma functions, right? So again, this is our reference point, highlighted in blue in the video now. Y theta minus b of theta alpha of 5, c of phi comma phi, and I have this gamma function. So this is the gamma function out here. Again, I do take logs to differentiate, to separate these terms out, which gives me that theta into log of lambda plus that theta minus 1 into log of y. So this actually happens when you separate it out, minus lambda y minus log of gamma of that theta, and then logs are invertible, so this function comes to e to the power log of that itself. So e to the power log of itself. So log of itself was this term in blue. Now, so these terms were the log of fx, and then the whole term becomes fx once again. And now I know that the term with y should go to yeah. So then I set these terms. Yeah, I set these terms to comply with this. A quick thing here, y with theta and d with theta, and then we have a c of y comma phi. We do have a c of y comma phi out here, which is this point where we have, and if we take lambda as theta, then y theta becomes lambda minus lambda into theta, so theta is minus lambda. D of theta is, well, it's that theta into log of lambda, but minus lambda, so it's that theta into, quick check that this is equals to this. Wait a second, things should be clear. Yeah, so out here I'm trying to do a couple of things. First, I need this highlighted function in the form of blue. So for that, I select the term with y. I'll try to get this in a natural form. So where I get theta is equal to minus lambda, because the term associated with linear y is theta, that's minus lambda. And then I set the other term with y, that's log of y minus 1, as c of so we put this term in the C term, and this is our A and B. Now we need the mean. Mean, for means we use okay. So spend some time on this. How we actually parse these parameters, where theta log of minus theta comes this. So we parse these in terms of our blue formula. So that's a practice, that's a habit you'll have to develop yourself. For doing this in some time of your life, you'll have to justify these functions, so it's better you get into the habit. These are easy calculations. And then you know the C term, the A term, the phi term, sorry, the theta term and the d of theta term, which is basically this. Yeah, Sorry, I didn't do this before, but now it looks okay. Now it should look okay. Right. Yeah, cool. So this is where I was taking the logs and then inverting the logs to get the function back. And here in blue are our parameters theta. There could be an imaginary term, so there is an I could have do this as well, and y. Okay, this was not an imaginary term, this was yi and theta I subscript I. So these are how they should look. Y theta be a function a of phi, y comma phi. So here we have both the phi, y, and yeah, c function. The only thing which are 1 are phi and a are both set to 1. C is there where we club these two terms, and then we have, so why are we doing this? We are doing this for analytical ease, so as to say analytical ease. And then we use a lemma, right? So what's the lemma? For finding out expectations and variance of a natural exponential distribution. So what's a natural exponential? A natural exponential is a function. I have definitely kept this to give credits to the original author, whoever took the pains to save our pains. So a natural exponential can be written, you can see this form kappa. So what they have done here is, you remember my y into theta by a of phi. So they have made y by a of phi equals to s of y into theta, just for a namesake. And then the b of theta by a of phi becomes a kappa of phi, and then c of y. So they say, like in our case, we have a natural exponential. This family, this class of function is a subclass of the class of exponential families. So this subclass can also be called the natural exponential family, in which the y terms are only y. A, they are linear. B, they don't have any other time. So it's y into lambda. Sorry, it's y into theta. It's that form. So the form we had here, which is y into theta, and if a of phi is 1, then we have a natural exponential family. So if this is 1, we have a natural exponential family. Look at the function out here. We have got a natural exponential family. So leave it out there. It will create confusions if I change it then. But I have written it once again for you. A of phi equals to 1, they belong natural exponential distributions. Family of, yeah. Thus letting kappa we have equals to E of y. So this is a theorem I was talking about, this lemma. I'm deselecting it so that you can have a look at it. So suppose x is a random variable which has a natural exponential representation, the moment generating function, and then you can get the expectations from these first derivative, second derivative minus first derivative is variance. So you can get these mean and variance properties. That's probably what your instructor wants when he has asked us to do this. The proof is nothing much complicated. All it requires is a differentiation and integration by parts, but we can leave it for the moment as long as we have the lemma out here. For the link, yeah, this is the link. If you can't see, it's stat.tamu.ad by Suhasini. Suhasini is the faculty who has created these notes for us. She needs credit. But yeah, this is pretty much what we do. So this is the lemma. Thanks to her for having typed this much of well-typed text. This was very hard. I have been doing this for the past 2 days. I know how much time it takes to type this stuff. So now we go to this part where we have our b of theta. Let me remove the highlights so that it helps. So b of theta is log of n into log of 1 by e to the power theta, and our theta is, again, what is our theta? So we'll do this substitution. So first I find b prime of theta, and then theta prime. Sorry, we don't do theta prime. B prime of theta. So that is what is meant by kappa prime of theta. That is first differential of kappa with respect to theta, which is again b prime of theta, which gives us something in terms of theta. How do we get it? Again, I look at this. So n by 1 by 1 by 1 plus, sorry, n into 1 by n into 1 by this. So n into 1 plus e to the power theta comes above, and then in the denominator we again need to differentiate this part, which is the chain rule basically. So when you have something in the product form like this, the part I've selected, apply the chain rule, which is n into 1 by this, which is nothing but differentiating the log part of the function which contains theta. There is also a separation part. So when I wanted to say the chain rule, I am talking about the blue highlighted part. This is differentiation by the chain rule where you do a plus. So d by d theta of n is 0, so that term vanishes. The second part of the term is n into the chain product form of differentiation of this with respect to theta. So it becomes n into 1 by and then this term, which basically shifts the 1 plus theta in the numerator, and then basically this n into 1 by 1 plus theta, and then we again differentiate this part going inside the function when you have a function of functions. So which is nothing but this. When you are differentiating this part, which was the part inside the logarithm, you get into 1 minus these are elementary rules of differentiation. So there is a negative and there is a plus into again the e to the power theta is, you do a differentiation of this part, which I again highlight in green because there is a subtail where a 1 becomes a 0 and then plus, okay, it's, yeah, plus this whole square into again this part. So when you differentiate this part, this one part becomes 0 in bracket, and then again you have this as the final result. So this is nothing but the chain rule. So you differentiate this again. After you differentiate the log, you get this, and when you differentiate this again, you don't differentiate this again, you have differentiated this to get a this, but then you are doing with respect to theta. Then you look at 1 plus the function in the denominator which you were treating as x to get to this part, 1 by x square, 1 by x, dy dx of 1 by x equals to 1 minus 1 by 1 by x square. This is basically going elementary to come here, and then this is 0, so you come to the e to the power theta, which is e to the power theta. So it comes as n into e to the power theta by 1 plus e to the power theta. Substituting this using the value of theta, that was log of pi by 1 minus pi, and I have told you that log is invertible, so e to the power log is the function back itself. We get this part, so the denominator rolls back to the numerator like this, and you have this part, which simplifies to n into pi, which we know otherwise as well. Now the variance is b double prime theta. So while doing this, what I meant to show you is easy mathematics. Easy mathematics in a sense that smart calculations help to reduce a lot of computation time. So what I'm doing is, instead of going back and doing the entire thing once again, I am actually starting here, which I will now mark in red in half of greens. I'm starting here, and I'm trying to differentiate the red letters with respect to theta, which gives me, so there theta in the numerator, there's a theta in the denominator. So I'll have to do the differentiation by parts when it comes to products. It's now not a chain rule anymore, hopefully, which we had to do if we were doing the double integration from the original b double prime. So then just copy it. So when you are differentiating the denominator first, so it becomes 1 by 1 plus x square, 1 1 by x square. 1 d by dx of 1 by x equals to minus 1 by x square. So first I write the x. Yeah, first we write the wait a minute. Yeah, sorry for the confusion. This is what happens when you are doing these kind of dirty maths. So yeah, so you can see there is a numerator and there is a denominator. So when I'm doing it by parts, I have to do I don't have to do anything. There are no compulsions, there are ways to do it, but I find this way easy, so I'm doing it in this way. So d by dx of 1 by x, so we first take this as an x, and we don't differentiate this because of the chain formula. So d by dx of 1 by x is minus 1 by x square, that's what we have, minus 1 by x square into, okay, but then that's not complete because there is an x out here which is not our x, we are differentiating it with respect to theta. So we have, so remember that this is not in this, so this was our x, this was 1 by, yeah, so I use the formula of this which comes here, but then I have to differentiate this term with respect to x again. You can Google the chain rule of differentiation for a formal representation of the chain rule, but yeah, that's pretty much, this is where it comes down, and then I have to differentiate this, which gives me to the power theta again, and then I differentiate the numerator, which is nothing, n and e to the power theta. Since we have already had the theta, we can't go further by this constant. And then I start replacing our thetas with pi by 1 minus pi, and again we find out a smart way to do it. We have already known this equals to n pi. This part in red is equal to n pi, so I do the n pi out here, and then I do the dirty to the power pi substitution for here. How do I do it? This part is 1 when I take this term as common between these two terms, and this part is nothing but e to the power theta, which is pi by 1 minus pi, and 1 by e to the power theta whole square. So that gives us as 1 minus pi again whole square, and this is 1 minus pi. So okay, that's not what it comes. It comes as something like, when we take this as common, this is 1, and this part which is highlighted is 1, and this part is only e to the power theta by 1 plus e to the power theta, because we are taking this term as constant. You see, the video gets so long. That's why these are left as an assignment, so that you pick up these while doing on pen and paper like this, and you get this becomes 1 by 1 minus pi, the 1 minus pi term gets up, and this is pi by 1 minus pi, these cancel out. and we are left with 1 minus pi, which is the variance that we well know of. Similarly, for the since our gamma is also a natural exponential function, we get expectation of y as straightforward because our expectation of y is b prime of theta, but we have set our b prime to be var theta log of minus theta, and this concurs with the formula how functions derivative. This is the standard form of the canonical link and the variance of the link function, because from here you can go back. Comes to this, I don't know what it was been said. Yeah, I'll be putting up the link for one part B very soon, which talks about the GLM. I hope you can do it by yourself. I am putting a link of this document on the web, and do drop me a message if you can't get a specific part right. Try to do it yourself. That's the idea. That's the idea why I'm not giving it to you. Thank you. Thank you for choosing me. I hope we will be more punctual very soon, because the season is quite coming in control, and I sincerely hope that you can get this. If you can't get this, let me know. I'll be sending you the document, and I'll be also finishing off the rest, but I'll be finishing off what I have on my mind is finishing off parts of specific parts of the rest of the problem, so that you can do the others. The harder parts I do by myself, so that you can answer the others by yourself and get in the habit of thinking the way, because when you're functioning in the industry, you'll have to talk about the functions, you'll have to talk about why you choose them and their properties. Anybody can ask anything as to why you are doing this, why are the formula, what is inside the black box, so as to say. And that's why these dirty bit of mathematics, this is where they come handy. Thank you for being with me, Marta. I hope I have been able to explain part of this to you today. And do drop me a message. I'll be definitely happy to do it to you. I might be charging a bit extra, because these are coming to be quite, in fact, very, very long calculations and extremely typed paper. I can't say that it's hard typed, it's extremely typed papers. So I might do it for you, because we all have the first time to learn it. So this is your first time, and I hope you'll be doing better soon. Thank you. This is Shubhradip Sengupta, your tutor, and you can always reach me